Today we are going to see about let A be the densely defined linear operator with a non-empty resolvent set, that is rho of A. The initial value problem given here is d of u of t divided by d of t equal to A into u of t and u of 0 equal to x. It has a unique solution u of t which is continuously differentiable on 0 to infinite limit for every initial value x belongs to d of a if and only if a is an infinitesimal generator c not a semi group of t of t. So let assume that d of a is a dense in x, and I also assume that rho is non-empty. A is an infinitesimal generator of the semi group t of t. It follows that x belongs to d of a. If it is infinitesimal generator means it follows the condition that x belongs to d of a, t of x belongs to d of a. D by dt t of x can be written as a into t of x, t of t ax. So t of t is the unique solution for the equation d of u of t divided by dt equal to a into u of t greater than 0, u of 0 equal to x with the initial value problem that x belongs to d of a. Okay, moreover t of x is continuously differentiable. From this it is continuously differentiable 0 less than or equal to t less than infinity. Okay, conversely we have to take that the equation that a unique continuously differentiable solution on 0 comma infinity is every in continuously differentiable with the initial data x belongs to d of a, and we have to prove that is an infinitesimal generator of the semi group of t of t. First we have to prove that we assume that the unique continuously differentiable solution, and then we have to prove that t of t is the c naught semi group. So first assume that every x belongs to d of a, which the initial problem that is continuously differentiable solution on 0 comma infinity we denoted by, it is denoted by u of t comma x. Okay, then x belongs to d of a. X belongs to d of a means we have to define a graph norm that is mod of x of g equal to norm x plus norm of a of x. So that is rho of a is a non-empty, a is closed, and therefore dA is endowed with the graph norm in the Banach space, which is denoted, that is d of a is endowed in the d of a is endowed in the mod of d of a, that is Banach space. Let t of t not be the Banach space of the continuous function. X of t naught be the Banach space of the continuous function from 0 to t naught into d of a with the usual supremum norm. With usual supremum norm it is continuous function. So let us consider the mapping. That mapping is from d of a to x of t naught. Okay, x of t naught defined by, it can be defined as s of x equal to u into t of x 0 less than or equal to t less than t naught. From the linearity of that initial value, the uniqueness of the solution is clear that s is the linear operator defined on all of d of. Here s is the linear operator that is defined in the Banach space of d of a. The operator s is closed. Indeed, x is closed means that xn tends to x in d of a and s of xn tends to v in x of t naught, that is x of d of a to x of t naught. Closed means xn tends to x in d of a and s of xn tends to v in x of t naught. Then from the closeness of a and using the initial value problem, d of ut divided by d of t equal to a into u of t, that u of 0 equal to x. Integrating from 0 to t, 0 to t means a into u of t comma x and d of tau. So if we substitute means integration and differentiation are getting cancelled. U of t comma xn minus u of 0 equal to 0 to t a of u of t comma x and d tau. You know that u of 0 equal to x we define this in the form of n. So u of t of xn minus x 0 to t a into u of t tau of xn d tau. So u of t to xn equal to xn of this term. If n tends to infinity means our this is considered as v of t x plus 0 to infinity a into v of tau. So which implies v of t is this one. The graph is closed means by closed graph theorem it definitely it will be bounded. So we consider the graph, so it is closed means definitely it will be bounded. So norm t of x less than or equal to k into norm x. By the graph we substitute instead of x u of t comma xn of g. You then if we take the norm for this one means graph theorem for this one means u of t comma xn of g norm of xn plus 0 to t a of u of tau of xn d tau. So if we use the inequality to split the norm means less than or equal to, and we know that the s is the linear operator. No, here T naught is the Banach space of continuous function 0 to t into d of a with usual supremum norm. So del x of y, that function of x, is the supremum of u of x of that graph. So del s of x of y equal to supremum of 0 less than or equal to t less than or equal to t naught mod of u of t is to x of g less than or equal to, this can be written as c, and this is x of g because this is a norm denotation, and supremum of u of x of t less than or equal to c into norm x naught, usually the same as it is. We define a mapping that t of t is from is d of a to d of a by t of x equal to u of t of x. Okay. U of t of x. From the uniqueness of the solution, that readily t of t has a semi-group property. So that 2, what is the equation 2 here? Here the equation 2 supremum. Here the equation 2 is supremum less than or equal to c into mod of g. Supremum, it follows readily that t of t has the semigroup property, and that for the limit of 0 less than t less than or equal to t naught, t of t is uniformly bounded. So uniformly bounded from that theorem. So let t of t be a C naught semigroup. If there exists a constants omega greater than 0 and m greater than or equal to 1 such that norm of t less than or equal to m into e power omega t from the limit of 0 less than or equal to t less than infinity. So generally we know that t of x can be written as multiply and divide by t of t naught of n, so it will be minus n t of t naught, and can be taken t minus n of t naught power n. So it is between the limit of n of t naught less than t less than n plus 1 of t naught be the semi group of that Banach space d of a. So if we take the closed graph on this form, norm mod of t of g, we get that it is x plus a of x. Instead there will be t of t, so less than or equal to norm t of t norm x plus norm of a of x norm t of t. So take t of t as common means we get x plus, this is in the form of closed graph, that x of g. So that t of x of graph less than or equal to m into e power omega t mod x. So we prove that is a bounded in the form of bounded. So now what we have to show means a of t of ay equal to a into t of y belongs to d of a square. So setting, what we set means v of t equal to y plus integral 0 to t. As usual we said that u equal to y equal to here y plus 0 to t u of s comma ay of ds. If we take the derivative means it will be 0, and if it will be 0, and this will be as u of t comma ay. Okay, the derivative and this get cancelled, and the left of the term is 1, this one, if we substitute the upper limit. So here what we do means, if we take the form of ay, if we substitute the equation of u of t comma ay means ay plus 0 to t a of u of s comma ay ds. Okay, then what we do means, if we take a as common means y plus integral 0 to t u of s of ay ds. So it will be in the form of v of t. So if v of 0 equal to, there we see that u of 0 equal to x, here v of 0 equal to y because we take that in the form of x. From the uniqueness, v of t equal to u of t comma y, so a into u of t is to y equal to v dash, and it will be also same as u of t of ay. So both all the terms are same. Now d of a is dense in x, and our assumption it is that the resolvent set is non-empty, and also d of a square is also dense in x. So if lambda non-empty means there will be a one element, that is lambda naught belongs to rho of a, and the lambda naught not equal to 0 means let fix y belongs to d of a square. If x equal to lambda naught I minus a of y. We assume that x equal to lambda naught of I minus a of y. If t of t, multiply t of t means we get the norm means norm of this term. We wrote this as norm of c. This is t of y. T of t is known as e power omega t, and this is norm y of g, because t of x of g m into e power omega t x of g. Here t of y means nothing but t of y is e power omega t mod y of g. Okay, then y of g can be y plus ay. This is less than or equal to c2 of if c2x, if we substitute means c2 e power omega t norm x. So t of t can be extended to all x by continuity. So by t of t we can extend from x to all x by continuity. As after this extension t of t becomes the semi group on x. To complete the proof, we have to show that a is an infinitesimal generator of t of t. So for that we denote infinitesimal generator of t as a1. X belongs to d of a. Then by the definition, t of x equal to u of t of x. Then by assumption, take the derivative means we get this, and derivative will be a1 d by dt of a t of x, and it will be if we take the derivative means it will be definitely ax. So obviously that a1 is contained in a from 8. To prove the inequality of inclusion, we let real of lambda greater than omega, let y belongs to dA square. It follows from 4 that a1 is contained in a. So e power minus lambda a t of y will be taken as e power minus lambda t of t ay, e power minus lambda t of t, because a is contained in a1, so a1 of y. Integrating from 0 to infinity means 0 to infinity e power minus lambda t a into t of y dt, 0 to infinity e power minus lambda t of t a1 of y dt. So a is closed by the definition, it will be obviously 0. So a into r of lambda a1 of y can be written as r of lambda a1 of y, and also we know that a1 r of lambda a1 of y will be r of lambda a1 of y. Okay, for that a of r of lambda a1 of y will be definitely equal to this term, definitely equal to this form of a1 of r of lambda of a1 of y. Okay, that y belongs to d of a square. Since a1 of r of lambda a1 are uniformly bounded in and a is the closed and d of a square is a dense in x, it follows that r of a of r lambda is to a1 of y equal to a1 r of lambda a1 of y for every y belongs to x. Okay, then this implies that d of a is the domain of domain of a is greater than the range of r of lambda a1 equal to d of a1. Okay, that means a contained in a1. From this 8 and 11 we obviously saw that a equal to a1. So this completes the proof. Hope you all understand, and thank you.